Quantum thermodynamics is a revolutionary field that merges the classical understanding of thermodynamics with the perplexing behaviors observed in quantum systems. Traditionally, thermodynamics describes how energy moves, changes form, and increases entropy or disorder in large systems. But quantum mechanics, which deals with the smallest building blocks of reality, introduces new dynamics such as superposition, entanglement, and coherence, which fundamentally challenge classical assumptions. For example, in quantum systems, particles can exist in multiple states simultaneously, or share information instantaneously across vast distances. Experiments with cold atoms and superconducting circuits show that these systems can temporarily defy entropy, a phenomenon impossible in the macroscopic world. This discovery has profound implications for energy efficiency and information processing, as quantum systems can store and transfer energy with unparalleled precision. Understanding how these principles apply to biological and cognitive systems raises exciting possibilities. Could the brain or consciousness operate within the rules of quantum thermodynamics? This connection lays the groundwork for exploring the energy dynamics of awareness and the role of focus and memory in maintaining order within the mind. The human brain is an unparalleled energy processing machine, consuming roughly 20% of the body's total energy despite its modest size. It operates with extraordinary efficiency, performing billions of calculations every second to manage everything from basic survival functions to abstract thought. At the core of its energy economy lies glucose metabolism, which powers synaptic activity, the transfer of information between neurons. However, emerging research suggests that the brain's energy efficiency may extend beyond classical biological processes. The controversial Or theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, posits that the tiny structural components of neurons could enhance the brain's computational power while minimizing energy loss. Though the theory remains debated, studies on the brain's capacity to process massive amounts of information in real time support the idea that it uses energy in ways that resemble quantum systems. For instance, the rapid integration of sensory data, memory, and decision-making hints at a complex interplay between classical and quantum-like dynamics. This hybrid model of the brain as both a biological and quantum energy system highlights the precision with which it manages resources, creating the foundation for conscious thought and experience. Focused attention is a cornerstone of conscious experience, and its mechanics reveal fascinating parallels with quantum thermodynamics. Attention involves directing energy toward specific neural pathways while suppressing irrelevant activity, a process that reduces cognitive entropy or mental disorder. Neuroscience studies show that when we focus on a task, regions like the prefrontal cortex and parietal lobes become highly active, while unrelated neural circuits quiet down. This selective activation mirrors the principle of quantum coherence, where a system maintains order by aligning its components toward a single purpose. For example, mindfulness practices have been shown to increase neural efficiency by enhancing connectivity between brain regions involved in focus and emotional regulation. From a thermodynamic perspective, attention is an energy-conserving mechanism that counteracts the natural drift toward mental noise. This explains why sustained focus can feel mentally exhausting. Maintaining coherence requires continuous energy input, much like isolating a quantum system to prevent decoherence. The act of collapsing mental possibilities into a singular focus is akin to collapsing a quantum wave function, suggesting that attention may operate at the intersection of classical and quantum dynamics. Memory is another example of the brain's remarkable energy management, balancing the need for information retention with the constraints of energy availability. At its core, memory relies on synaptic plasticity, the strengthening or weakening of connections between neurons based on experience. This process, while energy-intensive, is optimized to ensure that only the most relevant information is encoded. Recent theories suggest that quantum principles could enhance this efficiency. For instance, quantum thermodynamics posits that systems can store maximum information with minimal energy when coherence is preserved. In biological systems like the brain, coherence may manifest in the synchronization of neural oscillations, which coordinate activity across different brain regions. Experiments on quantum computing provide a compelling analogy, demonstrating how entangled states can encode vast amounts of information without exponential increases in energy costs. The idea that the brain employs similar mechanisms could explain phenomena like the rapid retrieval of complex memories or the formation of vivid, emotionally charged recollections. If true, this would position the brain as a hybrid system, leveraging both classical and quantum principles to optimize its memory processes. Conscious awareness, while fundamental to the human experience, comes with a significant energy cost. Unlike unconscious processes which operate automatically and efficiently, awareness demands heightened neural activity across multiple brain regions. Functional MRI studies reveal that tasks requiring conscious thought or decision-making lead to increased metabolic demands in areas like the prefrontal cortex, which is responsible for executive functions. This heightened energy use mirrors the dynamics observed in quantum systems, where the act of measurement or observation alters the system's energy state. In the brain, awareness can be likened to a measurement process that collapses a superposition of mental possibilities into a single, coherent experience. This collapse requires energy to overcome the entropy associated with competing neural signals. Interestingly, practices like meditation and mindfulness have been shown to reduce this energy cost by training the mind to focus more efficiently. From a quantum thermodynamic perspective, awareness is not merely a passive state, but an active process that shapes the brain's energy landscape, reinforcing the idea that consciousness and energy are deeply intertwined. The intersection of quantum thermodynamics and consciousness opens a new frontier in understanding the mind and its potential. If the brain operates within these principles, it suggests that consciousness is not a static byproduct of biology, but a dynamic process shaped by energy and information flow. This perspective could revolutionize fields like mental health, where treatments might focus on optimizing the brain's energy dynamics rather than solely addressing chemical imbalances. It also has profound implications for education and productivity, as techniques like mindfulness and biofeedback could be used to harness the brain's quantum-like efficiency. On a broader scale, this understanding could inspire advances in artificial intelligence, where quantum computing models could replicate the brain's ability to balance energy and information. Philosophically, this framework challenges traditional notions of consciousness as purely physical, suggesting instead that awareness might be a fundamental aspect of the universe's energetic fabric. This idea aligns with ancient spiritual teachings that describe consciousness as the source of creation, offering a bridge between science and spirituality. By exploring the energy of awareness, we not only deepen our understanding of the mind, but also glimpse the profound interconnectedness of all things.